What's up, my people? How you doing? How you doing? I hope everybody's doing well, staying healthy. Yeah. Um. Yeah. Today was pretty good. I actually feel a little bit better. Want to give you a heads up about later in the week. I'll probably do these kind of things most of the week. When I spoke with Mr. Roberts, he talked about being out 5 days. So I don't know exactly where that starts, but it probably just safe. I don't want anybody to get this because it just depends on your physiology whether you do well with it or not. I mean, it's not kicking my butt too bad. Feel a little bit more energetic than I did yesterday, um, and so um, yeah, we'll probably do these most of the week, and then we'll start doing some more interactive stuff. Now, I already had an appointment set for next Monday down at University of Cincinnati. Check out this ear thing and see what's up with that. So, let's see. Yeah, I was going to be out that day anyway. So I'm assuming everything will go well with this COVID crap. And then it should be the first day that I see you guys should be Tuesday. And then I'll be in for the morning classes, physical science on Wednesday. I'll be around, but I have to do a video conference um, at 11 um, related to some family stuff. So on 11 on Wednesday. So afternoon, folks. I won't see you then, but then I'll see you Thursday. So I wanted to go through just the last little bit in this unit. There's one more thing we got to deal with. I'm sitting here thinking how we're going to handle that because really it was more interactive. I'll probably just send you guys some notes. So I'll send you guys some notes and then I'll walk you through the PowerPoint. Like we did with solids, liquids, and gases. We'll do that, and I'll just kind of teach along a video, and we'll do that. Only this one's going to be about how energy moves, and it's stuff you had before. I'm just bringing it back up again. And you may not have been, Mr. Traven, you may not have been able to fill it out. If there's any questions on your review sheet, I don't remember. Natalie may know, but I don't know. Abra, you're gonna have to ask Abra too. If you're in fourth period, ask Abra because she knows all about this stuff. Yes, you do. Don't even look at me that way. So anyway, let's go. Let's see. See, we did the stuff yesterday on a page, and it kind of really depends on how big you wrote. I'd like to do it on the same page, but I don't think that's wise. So let's do this on the next page. Let's all do that. Now you got to do it on the same page. Make sure everybody holler out. You're gonna have to help each other. What page is the next open page? I think it's page 8, maybe. But you're gonna have to help each other out and holler out and determine what page you're writing on. If you end up having to skip something, skip a page, do it. Let just everybody get on the same page. Literally, I'm not joking. Every class, you're gonna have to determine what page you're writing this on. Okay, the next available clean open page with nothing on it. So you're gonna have to do that. So Max, you take care of that. Make sure everybody's clear. Okay, Mason, you make sure everybody's good on that side of the room. Yes, I'm talking to you, sir. Yeah, make sure everybody's clear on it, okay? All right, so here we go. 5 assumptions, and I'm going to show you the way that they're written out and kind of walk you through them, and then you're going to see below them what's written in red. I kind of simplified it. So all I'm suggesting is you write this on red. Now, when we get done, I'm going to write this down too so I don't forget it. If there's something that we need to write down, when we get done writing all 5, we're just going to write them out as sentences. When we get done, let's draw a line across the page. So I'm going to do this. I'm going to 5 assumptions. Okay, 1, 2, 3, 4, 5, and then we'll draw a line in the middle of the page. It shouldn't this stuff should not take you past the midpoint of page, I think it's 8, I think. And then we'll add some stuff onto the bottom. Okay. So I'm going to put that right here so I know what's up. And then when we come back tomorrow, we'll put stuff there. All right. Oh, that's what it is. I have a bandit hair. Oh, by the way, for my physical science classes, Damien Ibarra says hi. Yeah, he called me around lunchtime on his break. He's doing electrical stuff because he got, much like Eliza got the certification for, for vet tech. He got a certification for electrical stuff. So he's doing wiring, and he's at a shopping mall in Sarasota. But he sent me a text message just asking how things are, and I said, I'm actually home, so call me Boogerhead. And he did. I didn't call him Boogerhead, but had a really good conversation. And he wanted me to tell you guys that hello, and pay attention and do really, really well, because what he learned in physical science, he's using every day in electricity. Particles and atoms, guys, we're going to go into electricity. And I reminded him, and I said, and just where did you learn about volts and amps and stuff? And he laughed. He said, your class, Mr. Dorton. And I said, yeah, don't you forget it, Bubba. Anyway, he's a good dude. Good dude. But he wanted me to tell you hi. All right, so here we go. 5 assumptions of the kinetic molecular theory. All right, here's number 1, and I'm pretty sure this is going to work. Here we go. They have to do with motion. You don't have to write this down. Have to do with motion. They have to do with molecules, which we've been talking about. Okay, and obviously it's a theory. And again, you don't have to write these down. Okay, it's a theory because we can't see them with our eyeballs, right? But we can state some theories based on the way that we see stuff behave. And for most of you guys, I mentioned that when I was young and went on my first camping trip, how I finished spraying myself with my mosquito repellent and just casually at about 9 years old threw the can in the bonfire. Yes, let's just say it was an explosive evening. Yeah, that was not good. That was not smart. Well, I didn't know. I mean, I just didn't know. I figured, well, I'll just throw it in there because I'm done with it. I don't know what I thought, but I just assumed. So, anyway, that's one example. All right, here we go. Here's number 1. Number 1, the theory goes that any gas is a collection of innumerable particles. Innumerable meaning we can't necessarily count them. There's so many of them that counting them would just be too laborious. And they're very minuscule. That means they're very small, which are known as molecules. And we went over that last Thursday, right? Molecules is more than one. Molecules is more than one, right? More than one atom. And according to Avogadro's law. Now, you don't know about Mr. Avogadro, but he comes into play later in chemistry. He came up with a way to divide things up mathematically, just on paper, in such a way that we can deal with them. He came up with what's called Avogadro's number that you deal with in chemistry, and that is a way of, you use his number and it has an exponent in it, and you take a very big quantity and it helps you divide it up. Okay? And so the main thrust of this whole thing, the main point of number 1 is gases are made of particles or molecules. There you go. That's all you got to write for number 1. Cool. Pretty easy, huh? I told you you'd like this. Only thing missing is cilantro and onions. Okay. All right. Just by myself, I'll be just making a thing. Right, Bandit? You like cilantro? No, he actually does not like cilantro. He's more of a hot pepper dog. All right. He's under my feet. Okay, here we go. Here's number 2. Now, wait. Everybody got number 1 written down? Brooklyn, you got it? Kaylee, you got it? Ryan, you got it? Robert? tell me you wrote this down. Write it down. Okay. Abby, holler back there to Izzy and make sure she wrote it down. Okay. Okay, here's number two. Here's number two. Okay, now I'm going to read it. There are no forces of attraction or repulsion between the particles. Doesn't appear to be that way. Or between the molecules and their surroundings. So this is kind of important when you're trying to predict particle motion. Okay, if you assume that there's no real gravity happening between them because they're moving. Okay, they're constantly in motion based on number one. Okay, and there's no attraction between the container and the particle of gas, right? It's not trying to cling itself to the container. You know, a bunch of oxygen in a tank that, oh, I don't know, you might shove in a shark's mouth. I'm just saying. Okay, so basically that molecules aren't attracted or repelled to each other or the container that they are in, be it a balloon, one of them big tanks. Oh, here's a good one. Gas tanks that people have sitting, you know, in their yards to provide gas for their stove and everything. Them great big tanks, you know. Remember back when I was a kid, the big company was Blue Flame. I don't know if that's still a thing up here or not, but the property that my mom's got, she lives in one trailer in West Union. She's got one trailer, and then there's always been, since I was born, this other trailer, you know, this mobile home. And there was always this great big tank. Had, you know, the brand name or the company name Blue Flame on it, and we'd have to get it changed out. So the point is, the gas that's in there isn't attracted to the container, and it's not attracted, the individual gas particles aren't attracted to each other. Cool? I'll give you a second to make sure you got that. Monty, make sure that everybody has it. Okay. Brooklyn, you got it? Melee, you got it? Okay. I'm just checking. Chloe, make sure that Luke's paying attention, because you know Luke. He's probably like doing trigonometry or something. Okay, I'm just saying, because he's a math dude. All right, here's number 3. Okay. Again, what has this whole thing been about? Particles and what they're doing, right? Here we go. The gas particles are always at straight, rapid, and fast and random motion, resulting in inevitable collisions with other particles and their surroundings that changes the direction. Here's your picture. When you break, you know, you set up a pool table up and you've got everything in a triangle and you break it, there you go. Great illustration of gas particles. It collides with its container, right? It hits the side rails, and all the particles, all the pool balls hit each other. There you go. Perfect. So in red, that's the real idea here. The particles' directions are changed when they hit each other and the container. Cool. And don't forget they are moving in rapid, fast, random motion. And just don't forget that. Okay. Got it, Rye? Right? Yeah. Hi, Ryan. How you doing? Yeah. Got it? I can't hear you guys say, yes, I got it. Okay. Thank you. Okay. I'm just making sure. You know, because we're new at this, and I'm just making sure. Okay. And Becky, you good? Okay. All right, everybody. Here we go. Here's number 4, and then I'm going to quit. And then you got to, you know, don't give whoever's covering for me today. I mean, just be really good with them. Show them what you got. Because I was talking you guys up to Damien. Okay, and you guys know. I talked about Damien. I said that's the guy you give the house keys to. Okay, you know who I was bragging about with him? You all. Sure was. Sure was. Yep. All right, so here we go. Here's number 4. Okay. Since the particles are spherical, right? Think of a globe, but think of it clear. Okay, that's a sphere, you know. Okay, they're solid and elastic. So if you can imagine a collision between two marbles, you know, they bounce off each other. even though those are solid, there's a recoil, there's a bounce back, or even two basketballs. I mean, it's not quite the best example. Two marbles are more like the example where they hit, boing, and they bounce off. That's what they mean by elastic. They don't just, meet each other and go thump, and now they're together. They don't do that. Okay, the collisions involving them are elastic in nature as well as hang on, let me rephrase that because I'm missing a comma. Since the particles are spherical, solid, and elastic, the collisions involving them are elastic in nature as well. Should have been a period there, or a semicolon. Okay, i.e., for example, their kinetic energy is conserved even after the collision. So here's the idea. Okay, this has some kinetic energy. What's kinetic associated with? Say it. Somebody tell the person. There you go. That's my team right there. Okay. They know what they's talking about. All right. So this has some kinetic energy. This has some kinetic energy. And after they bounce, they still have a good quantity of that kinetic energy as they move away. Yeah, the moving energy, usually measured in, well, I was going to say newtons, but that's true. That's not wrong. It's not wrong. It's a measure of force, which we are going to get into big time later on. Okay, so they really don't lose any energy. Like they don't hit and then bounce off and then slow down, right? Most of the energy that they were exhibiting coming together is the same energy they exhibit going apart. Ooh, that's a fancy way of saying that. I did good with that one. Let's go. Okay. Okay, everybody laugh. You're okay. All right. Oh, let's say, Max, you still with me? Okay, yes, there he is. All right, Max is with me. Brooklyn, make sure he's still with me. Thank you, dear. All right, here we go. Here's number 5. Okay, so the total kinetic energy of the particles is proportion, and you know this, think about my mosquito spray. The total moving or kinetic energy of the particles is proportional. It has a relationship to, mathematical, right? The absolute temperature, and that just means what the temperature is. Okay, so when you're writing the red, right, the gas's temperature and energy depends on the KE, that's kinetic energy, average of the particles of gas. So I wrote the inverse, inverse from math, I wrote the inverse of what number 5 says. Okay, because there's a relationship there, y'all. Okay, the temperature depends on the average kinetic energy. There's a relationship, okay? The average kinetic energy, which depends on the temperature, which depends on the motion, which depends on the, you see what's happening here? They're all related. They are tied together. So I lower one, I lower the temperature, and we know this, right? Solids, liquids, and gases. I lower the temperature, and the particles slow down, right? They slow down. So 5 just puts things in a certain order. I flipped it around in the red and phrased it in a different way. So there we go. That's it. That's your 5 basic theories of particle motion and energy. The 5 basic points of the kinetic molecular theory. Okay, and again, I pointed this out to you guys. The kinetic molecular theory says that all particles, regardless of the state of matter, are in constant, everybody say it because it begins with an M word and ends with an N word. No, not that one. And it has to do with things that are not sitting still. Yep, that's in motion. Right, cool. I hope you said motion. There's a lot of other words you could have said, but you get motion, yes. Okay. All right, Becky, you good? Maylee, you good? Got that? Gage, we all right? Yes. Yeah. Good. All right. Brooklyn, is Max still with me? Max, you better be with me, paying attention, boy. You better be getting all this down because I'm gonna grade every single word you're writing down. Not just you, it's everybody. You guys are actually building things in your notebook, and all of a sudden there will be a lot of grades show up like bam, 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 bam. But I've tried to make it very easy for you guys to follow along with. and still keep us moving with these videos. So unless the person covering the class has something more specific that they want to do, um, I don't know if Mr. Davis is covering, but he may want to go into some things a little bit more, kind of quiz y'all. I have no idea who's covering. Um, but I would say just give him some study hall time to get some things done, because I know work's probably piling up. And I will get another video ready for you guys tomorrow. And y'all, I hate to say it, but given my circumstances, I have to say, be safe, be smart, keep your hands clean, because I probably picked it up from someplace at school, a common surface, something like that. Because I really wasn't around a whole lot of people before I started having symptoms. But if you start feeling sick, you know, duck out, stay in touch with me, and we'll get you squared away. Don't worry about that. All right, you guys have a wonderful day. I'm really proud of how you're doing. Keep up the awesome attitudes, so I can brag about you even more. All right, I will see you later, and have a good one. See ya.